techniques that are involved in timber bridge construction that help promote longevity and reduce maintenance cost and improve load capacity. So that's kind of where we're at today. Bridges come in many forms. This is a bridge of sense. It's in Vietnam, and the government doesn't have the money to build a bridge across the river. The children on one side of the river that are in a village need to go to school. And so every year they equip them with a leather belt. And the leather belt is tied around their waist and then strapped across the guy wire. And they slide across to the school that they're going to and then drop into the water. Of course, the Crocs get a few of them every year. And that's called a risk assessment on behalf of the government. And these children are part of that risk assessment. There's no money to build a bridge, and we need to get them to school. It's the second best thing. This is another risk assessment. This is in Peru, where every year they replace this hemp bridge. And they have a festival in which they have the women get together and make themselves a new hemp bridge. And someone ties a small string around their waist and they crawl across this bridge because after a year it's about done. And it's quite a drop, 80 stories into the gorge. And they pull the new bridge across. And in this particular case, this bridge is low cost and high maintenance because it needs a new one every year. So that's another kind of form of bridges. And bridges serve for all sorts of crossings, whether it be cattle or horses or cars or trucks, you name it. Our timber bridges carry lots of passengers. In Calgary, this bridge is dedicated to the elk. They were crossing the Trans-Canada, getting hit. And so in this particular case, they built a bridge just for the elk. Getting the first one across was a bit of a problem, but after that, they kind of learned and they use this bridge and the trucks use the one behind it. This bridge here I went under many, many times. It's on the Pacific Highway in eastern part of Australia. And I crossed underneath this bridge, as I was saying, about 20 or 25 times before I realized that the only thing on top of this bridge is a forest. It's trees. And this $7.6 million masonry structure was designed and built to allow the koalas to get across the highway without getting hit. Now, they're yet to see the first koala go across, but hey, it's a good thought. So our bridges, that are owned by various groups and governments, these bridges, they look for longevity. They want things to last a long time. When you build a bridge, you want it to last a long time. And last week we talked a bit about that in terms of longevity and how people presume that timber bridges don't last a long time, which of course from last week, I remember, is just not the way it is. It's false. We're in bridges in New Brunswick, for example, where I am right now, that are over 100 years old, with an average age of timber bridge of 82 years old. It's older than most precast concrete bridges, which arrived on the scene in the 60s for the most part. So when people say that timber bridges don't last, that's just not true. What they do is they confuse the not last with maintenance. And when poor design characteristics and strategies are practiced, our timber bridges require more maintenance dollars. And that's what we're here to talk about today, is what can we do with design to improve those aspects of a bridge design. Forces in our bridges, come in many forms: tension, compression, bending, shear, torsion. This is a particular design function for a bridge. You have to think about lateral loads. In this particular case, the truck driver's not really looking at the clearance sign and bang. So, we get lots of different loads that go on our bridges, and they create problems for us as engineers. This is another one here. You can see, look, the dumps up on this truck. Did that designer count on that load getting into the bridge? Probably not. Loads come in many, many forms. As you can see, this is not hitting a bridge, but you get the point. When you're working around vehicles, there are lots of impact loads that can go on in our bridges. This is another one here. Our bridges suffer from the types of things that go on that create problems for us. This old bridge, you can see here, the driver's fined $11,400. He's crossing the bridge overloaded. It's a steel bridge with a wood deck, and it's gone. And it's part of the history of the community. So these bridges, carry and catch lots of different loads. You can think of this bridge here. It was restored and got fixed up, and just in time, because this is the day it was finished, its restoration. And this is the day after. This is the day before. This is the day after. So our loads are quite large, aren't they? When you think of this particular bridge, and lots of old timber bridges were built low for a purpose. They didn't want the debris field to catch. They wanted it to go over the bridge. As you can see here, these floods can create debris fields. And then there's other sorts of things happen to even new bridges when we drive piles and the tip of the pile doesn't get bearing, but instead lands in a gas pocket, and after a bit settles, and the first thing you know, the bridge is unstable and collapsing. So lots of different types of loads created by environments, created by truck traffic, wind, snow. A host of environmental loads have to be considered along with live loads and deads. These loads all create forces in the bridge system. There's a tension load where things are pulled apart in tension, or in compression where they're pushed together. Bending moments where we have a truck tire going across this girder, for example, creating a bending load where there's compression and tension couple created to resist the load, and a reaction force at the end of the girder. These girders and decks carry these loads, and it's in the design of these elements to withstand these loads that we find the issues relating to timber design. So this is a first example I'd like to draw. Typically, in most situations, we consider shear to be these sorts of forces. We have a reaction load here at the support. We have a wheel load up here creating this kind of sliding by one another shear force in the beam. But this is not the shear force that we consider when we're designing timber, for example. Instead, if you take an element that remains in equilibrium, it's the horizontal shear force that's created in the beam that governs with timber, not the transverse shear. And if engineers aren't aware of that, problems can develop. In addition, torsional forces, for example, on piles. If you have a batter pile that's on the outside of your load path, stopping and starting action, acceleration and deceleration loads, can create torsion from the cap on the outside batter pile. That torsion then translates to tension perpendicular to grain along a microfibril angle you see here, and voila, the pile splits in tension perp to grain as a result of torsion, and we have to go in with a new support. So these types of forces create the need for proper design of components in a timber bridge: the substructure, superstructure, and deck. The substructure, that's the part of the bridge structure that carries the load into the foundation system, into the ground. And that's a very important part. In a typical bridge that's up to, say, 30 meters clear span, the substructure can be 40 to 60% of the cost, getting the loads into the soils at the riverbank or the end of the gap that we're spanning. As you can see here, we have a back wall and a wing wall and a breast wall in the system or stem wall with footing. Then we have footing piles or sill piles, often called, in a typical cast in place, for example, abutment. A pier might take this particular look: a pier cap, the shaft, a footer, a pier nose, of course, facing upstream. The bent, another term for it, can be steel, it can be wood, it can be concrete. Doesn't matter. We have a cap, a brace, and piles that all form the bent. In timber, you can see here, this particular case, we either have a pile bent or a frame bent. And lots of times our pile bents decay at the splash zone, and we end up making frame bents out of them. And we use the pile stubs that are below oxygen level to build a sill, and that's the best way to then work forward. Oftentimes I'll hear engineers say, well, look, if it's decayed here at the ground line, we better go and dig the piles out. And you'll see engineers pulling all the timber piles out of the abutments or piers to get clean of them, suggesting that they're decayed or rotten. But the fact of the matter is that below oxygen, the piles are as good as the day they were driven, and nothing better to provide sill piles than right top stubs from the existing piles that were driven. So you see the cap, cross braces, our plumb piles, and our batter piles here, all forming part of a pier system or a tower where we don't have flow through, but we're crossing basically depressions in the ground. Of course, this would not be a good strategy if we ever had it in the river, would it? Superstructure, the next part of a bridge that we have in our systems, can come in many forms as well. We can have the girder under superstructures, where you can have round log, for example, or squared up log or dimension timbers forming girder under systems, like this one here, for example. And today in our girder under systems in our timber bridges, we often encounter problems where engineers have looked to increase the capacity of the superstructure to accommodate higher loads. When this bridge was first designed, it was designed for 12 tons. Well, as the loads increased over time, the engineers added more and more girders. When they added more and more girders, what happened? They took the loads from being on top of the piles and put them in between the piles without a thought to increasing the strength of the cap. The cap span or split cap span increased in a sense in the fact that the girders are dropped in the middle instead of just at the pile tops. So a caution there in terms of watching for shear effects in these caps is needed in timber bridges. Another form of our substructure under our girder is a framed bent. You can see this bent looks like it was framed on top of a series of mudsill piles, when in fact it wasn't. It was framed on top of 4 feet, a sub pile that went down to a pile block 4 foot under the frost line in Ontario. So don't just assume because you're seeing it that you're seeing a design that involves the use of either mudsill piles or the framing of an old pile bent, because lots of times the frame bents were built themselves on sub piles that only went down below the frost line. As you can see in many, many overpass bridges and the rail lines in Canada built the same way. So you see the superstructure here involves the use of girders that were, in a sense, cantilevered by the end of this last bent that's on each side of the track, where there are clearance issues or risk assessments by the major railways lead to the need to have adequate clearance. And so there's a height envelope and a width envelope that the train needs, particularly for double stacks, for example, where we look to have 23 feet, say, from the track surface, the top of the crown of the track, to the soffit height of this drop-in. So what do? They design a cantilever girder system where the drop-ins allow the freedom to be able to shallow up on the beam and take advantage of this mechanical opportunity. Trusses are also lumped in with the superstructure side. And last week I showed this picture of an old one, 100 and almost 40 years old, with your web braces, only the compression web braces with the X in the middle, and the compression cord and the tension cord with the hanger rods. These systems form the carry systems for our bridge superstructures. And this Dare truss, which was a Percy Allen truss with the compression webs and the cross web in the middle, a hallmark of a Percy Allen bridge, with the tension cord swapped out for an MC channel, is called a Dare bridge. Or a through a bridge here in Funny National Park, which is rebuilt after a fire. As you can see here, this Howe truss, a typical Howe truss, which many of the trusses for our covered bridges in New Brunswick are Howe trusses. You see this truss in British Columbia here, as I mentioned last week, with the bent metal, holding moisture. Oftentimes the worst thing you can do is put bent metal on the face of wood. You think you're protecting it from the environment, when in fact every day the metal sweats due to change in temperature. And if you don't have a gap created in there between that metal and the piece of wood, then decay can be accelerated. This Howe truss here is a deck under bridge, 156 feet long. It's in the CNR's system out at Dawson Creek. You can see here, these are big trusses, and these were restored, as I showed you last week. This arch, again, down in Amherst, another form of a superstructure that carries load a long distance. And the engineers of old, what did they know about these arches and trusses? Well, they knew that if they separated the compression cord from the tension cord by a big lever arm, that gave them the ability to span longer distances with greater loads with less material. And the whole idea of a truss is to get that mechanical advantage of moving the compression, separating the tension and compression cord by a big moment arm to give you the leverage, the resisting moment couple you need to get the big load across the bridge and go a further span. So you can see this old fellow here, nearly 50 years old, down in South Dakota, as I talked about last week, Keystone Wise Bridge. It's an interstate exchange, a very famous bridge. As I said last week, they wanted to take it out and put new ones in for $23 million. And when we finished inspecting the bridge, we could only find a few elements that were bad, and they're going to restore that bridge, these bridges rather, this summer for $3 million. That's a $20 million saving to extend the life of this bridge series. Decks, you know, they're transverse decks. You see here this transverse glulam deck going across here on the girder under is very typical. The panels lay on their side, and for engineers wondering about design, I've always chosen L2, all L2 design. That gives you the happy medium between coarse grain and fine grain. If you get too coarse chasing treatment uptake, then they crack and splinter. If you get too fine, the treatment uptake suffers. So a good happy medium on the design for these sorts of transverse deck panels. There's an all L2 mix for getting maximum uptake in terms of the weight. And pentachlorophenol, for example, the target would be 9 kilograms a cubic meter. And in terms of depth of penetration, you'd look on side grain penetration for incising 5/8 of an inch deep, and then a penetration of around 7/8 of an inch. People often see incising on these bridges in their design spec, and they think that the incising involves injecting somehow the treatment into the wood. And that's just a fallacy. What does incising do? And there are incising specifications. And in incising, what we do is open up end grain. End grain travel of liquids and moisture in wood is 100 times faster than side grain. And all an incision does is it has a roller that's got slotted tooth, and the piece rolls through this roller, and the tooth creates an impression into the wood, and it opens up end grain. That's what incising does to improve the uptake and depth of penetration. You can see another example of a transverse deck panel system here. You see yet another one. And in the transverse deck panel system in the deck systems, you'll notice that these gauge beams are very important. And the gauge beams help prevent the difference in deflection that occurs, which will lead to reflective cracking in the asphalt. People often talk about using dowel systems to join the panels, and I have never been a fan of those because the loaded edge distance of the dowel always creates a breakout problem, and it's best to use a gauge beam system. As you can see here, another deck system is a longitudinal deck system, where these are solid elements that are then have rods positioned full width of the bridge, and they're tensioned with a required torque. In this particular case, it was 560 foot-pounds, and it pulls these together, and the deck and the super act as one. And underneath the deck and super, here goes another substructure option, and you can see something I'm going to talk about here that I showed last week and didn't address it because it wasn't in the design side. You can see this crack here going on. You know, and what's causing this crack? What is it that's getting to this crack? So we're going to talk about that in just a minute, so keep that in your mind. So you can see this deck system here over this arch system underneath, and our columns all form part of that superstructure deck system that carry our load. So as we dive into the design properties now, what are the important things that I look to? Well, firstly, how do we design timber bridges? Well, I always tell engineers that you go to the local country or jurisdiction, you look for the bridge code, and within that there'll be a timber section. And in that timber section, what it does is it serves as a code to stand between the designer and the timber code. So in Canada, we have 086, you can see engineering design in wood. And what S6 part 9 does is it interprets 086 for the engineer as to how to use the timber code to build timber highway bridges. And the treatment code talks about what we do to preserve them with preservatives, pressure treating them. And then, of course, timber design guides, like the Canadian Wood Council guide, help engineers with ideas on how to do things correctly. Owner specification and standard drawings are all part of the package that's important for engineers today to design with timber. And this specification side is a lost art because there are just not many timber bridges designed anymore. Steel and concrete have taken the market. And as a result of that, just this last decade, have we seen timber bridges come back into vogue because of carbon trading and cost and a whole series of reasons that we talked a bit about last week. And so part of this resurgence or renaissance of timber bridges is the remembering, as it were, the proper specifications. So we're going to talk about that here just coming up. The bridge code, as you can see here, is S6. It's a Canadian Highway Bridge Code, and Part 9 covers timber bridges, as you can see here. And 086 covering design of wood, and the treatment code, and these design guides, and owner specifications, as you can see here. This is New Brunswick. Standard drawing packages, you can see here. And lumber grading. Now, what does a lumber grading mean? Well, if you think about it, engineers design timber bridges and then put specifications on drawings, and they go out to tender and contractors bid them. And what provides the liaison between the designer and the contractor? Well, it's in the lumber grading rules, because the engineer says what type of grade and species to use in a particular application. Then the contractor can go to suppliers who are using the same lumber grading rules to grade their timbers, and then the two meet together with the proper insertion. You couldn't have the engineer design a number 2 SPF girder to go on a bridge and the contractor not know what number 2 meant. So the lumber grading rules, NLGA, define these things for the suppliers of materials. And they allow the engineer to have in a sense, a meeting of the mind. There's a variety of properties that are important with timber that impact how we design with it that engineers need to know about. Number one that I always talk about is that wood is anisotropic. That means it has different strengths in different directions. It's different from steel. Steel is isotropic with a similar properties in all directions. And one of the worst things you can do is design timber as if it were steel. The next part of it is that wood is hygroscopic. That means that it breathes in and out moisture. It's constantly equilibrating with its surroundings. It's why your wooden rockers get loose in the winter. When you've got a wooden rocker and in January you're heating the air that's coming in from outdoors, it's cold. When you heat it, it can hold more moisture. When it picks up moisture, it sucks it out of the timber furniture, and they shrink and it gets loose. And so a bridge is no different. The average moisture content under an open deck bridge is 16%, under a closed deck bridge is 14%, and under a covered bridge, it can be less than that. And so wood is hygroscopic. It breathes in and out moisture, and when it does, it can shrink and expand. Further, because wood is hygroscopic, when we're buying large dimension timber like 8 by 16s or 12 by 24s for timber bridges, they're typically green. That means when you buy them, they're going to be over fiber saturation point, and they're going to be full swell. And when they dry out to the moisture content of the bridge, they're going to shrink. And if engineers don't realize that and consider it, it can be trouble in their connector designs. Species drive the property. Doug fir, for example, is generally stronger and stiffer than, for example, SPF. And the grade within a species is driven by the size and location of knots and so on. And that also impacts the property. So wood, as I said, is anisotropic. It breathes in and out moisture. It has 3 different directions. Longitudinal, where shrinkage and expansion is negligible. Tangential and radial. Tangential shrinkage and expansion is about double radial in our species in Canada. There are some species like ipe and icky wood, for example, where it's equal and it makes great dowels because it shrinks the same and expands the same in both directions. But this is what we need to be interested in as engineers, as we understand wood is hygroscopic, breathing in and out water, and as it does, changing in dimension. This moisture content can affect physical properties in addition to dimension. Moisture content, for example, is described as a percent based on the weight of the structure, and wood can be 180% moisture content. In other words, it's like a sponge on your sink side that goes dry. When you let it fill up with water, it can be 5 times the weight of the dry sponge. Well, some wood can be 180% moisture, more moisture in terms of weight than the wood. And so wood, as it shrinks and expands, is picking up and dropping off water. And as generally it goes down below fiber saturation point and gets below 29% MC, it tends to gain in strength and gain in modulus of elasticity. As you can see, as I said before, moisture affects shrinkage and swelling as well. It also affects the stiffness, toughness, and fracture morphology. So There are a lot of things that moisture impacts in wood, in addition to MOE and strength. Fiber saturation point, as you can see here in this slide, is the point at which the cell water, the free water, leaves, and bound water that's held in the cells is then begun to be is dropping off of the wood. So the free water leaves when it's all gone. That's cell lumen water. When it's gone, then the next water to leave is the cell wall water, and when that leaves, wood shrinks. It gains some strength, gains some stiffness, and as it drops in water content below 22%, then it becomes independent of decay, because below 22% wood does not decay. So water is very important in wood, and it's a very important part of any designer's criteria by which they design their wood structure. So variability within the species can also be a factor. Knots, splits, checks, slope of grain, grain density. These are things watched by the lumber grading agencies and will determine the grades in our timber, the size and location of knots, for example. In addition, there are differences between hardwoods and softwoods. If you have a maple corbel, for example, it's different than a softwood corbel. The hardwoods and softwood are different. Hardwoods grow in response to light. They're phototropic. And so slope of grain tends to be a bigger problem with hardwoods than softwoods. Softwoods, on the other hand, are geotropic. They grow in response to gravity. That's why if you go skiing on a ski hill, you'll see the softwood trees growing straight up and down. And the phototropic nature of hardwoods, they'll grow all over the place. They search for light. And so our softwoods have been generally used for building materials more because, one, you can drive a nail in it. It's not that dense that you can't drive nails in it. Number two, its slope of grain is generally better, and it's slope of grain that impacts the strength and bending of species a great deal. These grading agencies help us grade these timbers considering these knots and different distribution of knots. As you can see here, these sorts of grading agencies that we think about in North America today. So these grading agencies help us understand the size and location of knots. As you can see here, the top side specifying the size and grade of the knot. The impacts of decay on mechanical property are significant, and so designers have to be interested in decay when they're designing their fasteners, for example, with their timber bridges. And you can see these are the sorts of things that get impacted by decay. And next week during maintenance session, we're going to be spending more time talking about how these factors are noticed and inspected and what we do when we find it. Temperature, although not a big factor in timber, is a factor to the extent that when you reach over 150 degrees C, it will start to lose some strength, not really a designer's criteria. And at low temperature, if you're using green wood, it can be freeze that cell lumen water and lead to some breaks and shattering. And this is particularly typical in the Great Canadian North. Specific gravity, or better known as density. Specific gravity is a unitless number. It's the ratio of the density of the wood to the density of water. And we see specific gravity, SG, used around the world, so you don't have to know the units. And so we often think of specific gravity of wood in terms of moisture content, its highest being 0 MC, then air dry at 12, and service dry 19, and then FSP, or fiber saturation point, green. Now, people often think of the term kiln dried. They say, well, I'm going to buy kiln dried wood. Well, what does kiln dried mean? Service dry kiln drying is 19%. Why did they pick 19? Well, it was a comfortable range below 22% so that black spot and spores don't form. That was the reason for 19. In glue laminated beams, for example, they're produced at 12 to 15% moisture content. And that was a chosen reason to help cure the waterborne glues, and secondly, to be in the mid-range between 0 and FSP, so there's minimal dimensional change. In fact, a glue lam beam is perfect for bridges because it goes into service at about the same moisture as it's going to finish and equilibrate at, unless you make the mistake of using a waterborne treatment, which I do not recommend in glue lam, because that then if they're waterborne, that takes a dry glue lam and turns it into a wet one, and changes the way we treat it for design. The specific gravity of hardwoods and softwoods are these sorts of ranges. You can have actually some kinds of wood, like ironbark, that are dense enough to sink in water. They're 1.2 specific gravity, whereas Doug fir, traditionally 0.48 to 0.52, spruce, for example, Nova Scotia, 0.42 to 0.44, 0.45. Hardwoods, you can see the rest of them. So specific gravities are in a wide variety. Balsa wood, for example, or Western red cedar can be done in the 0.23, 0.28, 0.30. The strength then is impacted, as I said before, by knot, splits, checks, temperature, moisture, design properties, all impacted by these features. Bending, for example, in wood is impacted by knots. And you can think of it here. You look at this load head putting a load on this piece where the knot, even though it's in the compression phase, is still going to lead to premature failure. Why? Because in that particular case, the big knots are at the top, and you can see it here. And the big knots create slope of grain. And that slope of grain then creates tension perp to grain problems. As you can see here, this beam, this heavy dimension timber, is in upside down. Now, I was never taught at UNB when I went to school in my undergraduate, nor my master's, that there was an upside down for a large dimension solid sawn timber. But there is, because the grade rules allow a bigger knot upstairs. And the bigger knots, if they get turned downstairs, are going to create problems, as you can see in this girder right here, which is in upside down. So this knot is not, the knot isn't the weakness, because it's generally denser material. It's where there was a branch. What creates the weakness is the slope of grain around that knot. It's the slope of grain that's the problem. You can see these examples of slope of grain failure in girders. A situation where the designer might have specified a number 2, for example, and the supplier got the right wood, but then it got in upside down. And you can see what goes on. And the reason that a knot creates a problem is this. Again, contrary to popular thought, it isn't the knot. It's the slope of grain around the knot. And if you take and resolve the forces in tension to perp to grain and parallel to grain, it's the resolution of those forces that get you. Wood's weakest direction of strength is tension perpendicular to grain. In Doug fir, for example, 15 psi or 1 MPa, sorry, 0.1 MPa. And so if I have a knot, a big one, and it causes a divergent grain, the grain has a greater angle to the axes of the piece, and the resolution of the forces creates more tension perp to grain. And these failures you're seeing right here are not caused by tension parallel to grain. They're not caused by failure in the knot, because you rarely see the knots fail. It's the area around the knot where there's been a resolution to tension perp that creates the failure. And that's one of the big things about wood being anisotropic. We like straight grain wood, as you can see here, where the grain's pretty well aligned with the axes of the wood. Now, this tension perp also shows up in other ways. The girders are designed to provide lateral stability for the caps and piles at abutments. And these knee braces that are common in the prairies are not a good design. They're a poor design. They're a hand-me-down from years past because of the volcanic ash and the use of what? Drift pins all the way down through here, which lead to decay. The pile then loses its shoulder strength around the drift pin, and they start to bow inward because nothing's keeping this abutment pile bent from bowing inward toward the river. So they put, what do? A knee brace in here and notch it to cover the pile and the cap, and then tension perp takes over, and voila, you got trouble, as you can see here in this picture. Just a poor design. It should not be used. The way to handle this is don't put the drift pin at all. Use a proper horizontal bolting system to attach the girder to the cap, turn 90 and have a horizontal through this cap, a horizontal through here, and then here, do the same here with an angle bracket, horizontal and horizontal, turn 90. And that allows the system to stay in place. When you go vertical from the top with a fastener, you shorten the life of the connector by 2/3. That one simple change in your design, stop the use of verticals that originate from the top, will increase the longevity of your bridge by 3-fold. It's that big one right there that takes out most bridges. You can see here tension and compression parallel to grain serve a big role. You can see compression here of this column test where you can see this compression wrinkling, we call it. It reaches the yield point in compression and goes into plastic shift. And how does this surface out in the workplace? Well, this is a node and a compression web on that milkish inlet 3 bridge, and you can see what was the culprit. Knots are a culprit not only in tension, but in compression too. You can see a plastic shift right here in the surface, a plastic shift here, and you can see the separation of grain around this knot, and this corner piece is being impacted by this knot. Why? Slope of grain. So these factors all impact the design of our timber. You see this perp to grain failure from this load head where the wood is crushing perpendicular to grain. This is a bending failure under a load head for a round log girder. And this guy here is shear parallel to grain. Well, is this really shear parallel to grain? That's an interesting question. What does this look like? Well, you'll see here something very important. If you're out inspecting bridges or you're designing bridges and you see this, note one thing, there's an attachment. Shear is different from shrinkage. This is shear. 66% of all horizontal shear failures in wood occur in the late wood, early wood interface. That's when the wood starts growing in the spring, the cell walls are the thinnest, the lumens are the biggest, and its shear capacity is the lowest. That's where they'll be. That's where they'll focus. As you can see them here. This is a shear failure in a beam. This is another shear failure in a beam. And there, oh, that's a shear failure. Now people say, did that shear failure originate at the reaction? Well, these beams go by the support. As you can see here, they go by the support. And so shear is up in the upper quadrant and over where there's continuity over a reaction. Here you can see shear failure again with the sawdust at the bottom. Why is it sawdust? Because the two pieces of wood are rubbing together. And you often get shear failure in caps where you have pumpers. You can see a pumping pile creates a gap. We'll talk about that in a bit. And they're measuring them here, a 16th, a 3/16th, and so on gap. And when that happens, what happens is your shear span increases and caps can go to failure like this one here. And so in the industry, what did they do? They thought, well, we'll get around this horizontal shear failure and caps. We'll make them out of precast concrete. And there was a big move back in the 90s to do that. They're now taking them out of the code for the railway, for example. Why? Because they're so stiff that they move all the load out to the batter piles, and a 15-degree angle on a batter pile reduces a timber pile's capacity by 50%. And so they all take the cracking and failing as we move that load out because we put a precast concrete cap in there to prevent pumper action creating shear failures. You can see here, there's a shear failure. There's a shear failure. Is this a shear failure? No, it isn't. If you're out inspecting the bridge engineers or inspectors and you call this shear failure, you've done a disservice to the client. What is this? Well, that's tangential shrinkage. There's a boxed in heart likely inside that cross section, and it gets thin there in the radial direction, and the tangential is double radial. And what does it do? It finds a fault line. And what is that fault line? That's a ray. That's a ray that goes to the center of the tree, and as it shrinks, it separates at the ray, and that's a naturally occurring shrinkage crack already accounted for in the design values. And if you say that's a shear crack and discount the strength of your element, that's a big disservice to your client. You can see another one here, not horizontal shear failure, that's shrinkage. I had these sent to me to test one time at the lab. I put my credit card in there. I called the client back and said, look, I can test them for you to see if they're defective, but I know they're not right now. That's a normally occurring shear crack, shrinkage crack, and we do not need to test this piece. All wood develops shrinkage cracks. You can see this freshly cut piece here. Why does it shrink? Well, guess what? Tangential shrinkage is double radial, and it finds fault lines along the rays and opens up as it shrinks. And it doesn't shrink, remember, until it starts to lose cell wall water or bound water. Here's another shrinkage crack, sorry, a shear crack. Now, I want to show you this drawing. I wish I'd have seen this picture when I was in my undergraduate program. This is a big coal train going across Crescent Beach Bridge out in near Vancouver. And you can see here what's going on. This continuity wasn't considered in this interleaved girder system. There's 4 plies. Every other ply is continuous and one simple. And they didn't consider shear. And as a result of it, shear led to failure in the guy that was picking up the heaviest load. Who was he? The continuous element. When he fails the outside ones. And what is that white? That's wood powder that's being rubbed up and will oftentimes lead to fires because of if you have a unit train with a lot of action, this horizontal shear will rub and create heat, and those wood fibers can catch on fire. And what do they do to try and work them? They'll put what they call a sister girder piece across, which does nothing to deal with the situation. It actually covers up the crack. And what does it really do? It jacks all the track spikes up, as you can see here. There's another one here. Very common way. We'll talk about this more on the maintenance side next week. So this shear distribution at reactions is a pretty important feature. Engineers are taught to use 3/2 VA and neglect shear a distance D away from the support. Well, if you're using glue laminar continuous, you can use our shear volume now, and it's over 2 cubic meters. And so what do we see in simple sands and solid sawn? We see a lack of understanding about where shear is a maximum. Shear does not reach parabolic about the neutral axis, and 3/2 VA, which is the transformation of VQ over IT, it doesn't reach it until you get to about 2D. In this range here at the end of the reaction, it's parabolic. It's triangular, 4/2 VA, and the compression bulb that's here increases the shear capacity, which is why we see the neglecting of shear. But the maximum shear is really close to the bottom at the reaction in a simple point. This 4/2 VA was explained by Mandry, as you can see here is the reference to this. And he realized in 1969 through a series of tests that wood's horizontal shear capacity is up to 50% increased when it's associated with compression perp. Thus why we neglect shear distance D away from support. But shear is truly there about 2D away. And if you see a horizontal shear in a simple beam at this height, you'll know it's occurred usually more than 2D away and then run to the ends. In the Canadian system, we recognized this in our cantilever beams where there was no load on the cantilever, but yet it was failing in shear. The shear had its origins in where the load was, and it runs to the end, as you can see here. So now moving into timber connection design. Horizontal connections are the way to go. Vertical fasteners that allow moisture to follow the trace of the connector to the inside of the wood accelerate decay. In addition to that, I always specified pre-manufacturing post-treatment. The idea of treating timber and then drilling a bunch of holes in it on site just makes no sense to me at all. It's why my specs and designs always call for oil-based preservatives so that I don't swell the wood, because I can't pre-machine and post-treat with water-based preservatives because that swells the wood and my machining won't stay. And so I always specify oil-based treatments that fix to the cell wall. I always specify pre-machining before I machine my fasteners out in my design of kits. You can see here in a typical bridge. Look, this is a typical design series. You'll see that all over the place. It's why 82% of all bridge degradation is due to decay. Why is it? Because over the years, 100 years ago, what did we do? We drove verticals. Everywhere was easy to drive from the top. We just drove verticals, drift pins, look at them all. And if you look for decay today in existing timber bridges, where do you find it? Where the fasteners were, where the ambient water gets down the trace, hangs around a long time, and leads to decay, even in creosote-treated piles. And here's a pile example of just what I mean. The pile split off from the side because the drift pin connecting the cap to it has basically led to decay. Don't do that. Turn 90. Put side cheeks horizontal, turn 90. Side cheeks horizontal, turn 90. Side cheeks horizontal, turn 90. Like this. Like this. Don't go through the plank. Go down between it. Here's Randy fixing up a piece of milkish. It was one of my most complex designs of a connector I had. We have tension forces in this parent pair. We have a node block here with a single compression web coming down here. It's the king rod at the end of the span. So we've got tension in here. We've got a king rod, a node block. We've got a marriage block inside. And we've got all this action going on. And here comes decay. The moisture following down this vertical, getting in the middle here, decaying from the inside out. And we had to design a connector that would basically allow us to take both of these parents and amputate this piece like this as the first cord. And we'll do the same to the second cord at the same location. So we transitioned by with a Packer glue lam, a high strength fiber piece here. And you can see here we're doing in a bevel block. There's a bevel block. You can see it here. We're gluing it into place. Now we're going to put a tension splice cover plate on it. That's going on just as we speak in these days. And this will happen on both chords, allowing us to restore the tension capacity, the bearing capacity, the shear capacity. There is 9 different design bases for this connector. You see, if we don't watch these designs, what happens to our bridges? Well, this one burned down. You say, well, geez, it burned down. Well, you know, heavy dimension timber is a 1-hour fire rating. Why are timber bridges burning down? Well, CNR and others have learned they're rating their bridges fire stability against decay. The more decay in a bridge, the more fire prone it is. Wood that's not decayed has a fire ignition point of over 500 F, 512, 520, depends on the species. If you have decayed wood, frazzy wood, it can drop by 100 degrees Fahrenheit. Secondly, you got these fasteners that are going through the wood. They conduct thermal energy to the center of the wood where the decay is. And so that combination leads to bushfires to take down timber bridges. And so by controlling in our design, the way we design and using the proper fastener systems, we protect the bridge against fire more, we extend its life against decay more, and we build a stronger, more solid bridge. These are important. So let's look at a few bridge examples where we go to horizontal and everything. You see this bridge in Dickinson, you see this one in Australia. Everything switched horizontal. Don't drive a vertical down through here, horizontal it. Horizontal. And if you do go up, don't pass through the top face. Stay within the piece. So we allow for shrinkage in our timber as well. If you're putting green timbers, which is any heavy dimension timber that you buy in Canada, 8 by 12 or 12 by 16 or 12 by 24, these timber elements are going to be green. Even if they're creosote treated. You can't use creosote in New Brunswick and Nova Scotia, but even if there are in other areas, they're still going to be over FSP and they're still going to shrink as they equivalate. So what do? Is we make our connections with ovals. Everything, our side plates all have ovals. What does that do? It allows the wood to shrink and settle on itself as it dries out and equivalates with its surroundings. Everything needs to have slots like this so that the deck can shrink back and forth. You can see here, we have adjustments here for letting the deck move. And here you see horizontal with adjustments. You can see this guy here, I put him in on purpose to show this adjustment in this cheek on this lift bucket that allows the girders to be lifted up and down. And this I thought you'd catch. This is called shelf cutting the wrong material. You never shelf cut a glue lamp, especially a treated one. And you can see here it was done wrong. I put it in on purpose. Why wouldn't I shelf cut this? Well, you shelf cut hardwoods and solids on to cause the drip edge to occur in the heartwood. And that gives you more stability against decay on your end piece. But there's no sense of doing that in a glue lam beam because that's just not going to be the way it's built. In this particular case here, you can see these pieces are shelf cut. See the corbels here, they're shelf cut. And then we have a copper naphthenate treatment with 2% reactive agent and an anchor seal to prevent that's paraffin wax and water. And you can see here these adjustments, slope cutting, let the water run off, let the wood shrink and expand. These are all converted to, by going 90 with ovals, all the verticals were pulled out of this bridge and it was swapped out for a horizontal system. You can see here, and there's the diffuser we'll talk about next week for maintenance issues. You see the slope, the slotted attachment here. And these guys slotted so that this gauge beam can move with the deck. Attachments here so that they can be tightened instead of using these old track plates here. You can see tie plates. See here. So faster spacing, either end distance, edge distance, and so on, has often been a big feature. I was on the Northridge earthquake post-disaster analysis committee for technical activity committee at AITC back in the early 90s. And one of the things we learned there was that the glue lam beams didn't fail. They failed at supports because the shake and bake brought in acceleration loads and there was a plug pull out. These trusses and these elements would pull out, and thus brought in this whole discussion about shear plugging, which you'll see in the codes and standards today that apply to both shear plates, split rings, and bolt shanks. And so our end distances, both loaded and unloaded, edge distance, both loaded and unloaded, and our spacings are all geometries that have been established that allow engineers to help prevent shear plugging, maximize capacity without problems. And people often ask me, Dan, what about pilot holes? You know, the hole to hole, the shank diameter to hole diameter is a critical feature in a fastener. Engineers should spec the tight tolerance. You know, the Canadian code calls for 1 millimeter or 2 millimeters max. The way to calculate it for different diameters of bolt shanks is 0.92. You should have a bolt diameter that is greater than 0.92 of the pilot hole diameter. The design code values that we use today are based on 0.92 or higher. When you get down to 0.80 or 0.75 shank to pilot hole, what we call side frictional forces lead to cleavage in the pilot hole, and your reduction in fastener capacity is significant. So in your design specification and your designing of elements, you need to consider that. Now, this is an important one. This is a posting design with what we call a furniture joint. That's a lap joint, which is not a structural joint. And the river flows this way. And these bolts were put perp to grain, so they should never have been put this way. If they were going to use a bolt on a lap joint, it should have went parallel to stream flow, not perp to stream flow. And up comes a debris field, and bango, this guy was gone. Why? Because he was too big for this bottom stub. Bolts go in the wrong direction, and he had what? He had a lap joint, which is not a structural joint. As you can see here, this basically this drift pin has created decay, and here comes this angled brace, and he's pushing down on them, and grain separation takes over because of reduction of section. Often in the Maritimes, we get involved in cribbing, both open face and closed face. And we use a drift pin where we have a 0.9 drift pin diameter to hole diameter in softwood, and we drive these drift pins and these cribbings, and this is open face. And these drift pins are the start and the end of our cribbing. They let water into the untreated core. They're often built with CCA treated pieces. It's water-based. It leaches back out into the river. The drift pin lets the moisture into the brightwood, and the rest is history. And thus why people say you don't build with timber anymore, because things don't last and the maintenance costs are so high. That if we designed it correctly to last, carry loads, and go the distance, people wouldn't say it because timber bridges would be lasting longer than steel and concrete. In that Milky's bridge I showed you earlier, the worst part of that bridge was the steel. It was heavily depleted compared to the wood. And so wood will last when it's protected and designed properly. You can see the first impact of a drift pin. Decay gets in behind the treatment. It loses compression perp. A 10% loss in specific gravity due to decay leads to an 80% loss in compression perp, and we get what's called a compression bulge. And of course, that's the beginning of the end for your cribbing. You can see here going on. And what happens to the cribbing? Well, in this particular bridge in Nova Scotia, what went on? The whole bridge settled down, and we get a bump here on the asphalt above. So we don't like it. And of course, open face cribbing, only good to hold the big aggregate. The small isn't held, and we like to see a closed face because it holds the approaches better, because the fines is what is the glue that holds your aggregate base together. So this is the typical design that I would recommend to use instead of drift pins. They're easy, they're cheap. You can 6 mil plate thickness. You can have them bent with a welded cheek up top and put them all horizontal. This cribbing designed with these materials are going to last 3 times longer. Yeah, it might not be as cheap as driving a drift pin, but is it worth getting 3 times the life out of your cribbing? I guess so. So timber pile design is another one that you don't see a lot of work today on, because timber piles haven't been driven much in the last couple of decades, but that doesn't mean there aren't a lot of timber piles in service today, because there are. And, you know, in our timber pile design, we usually consider 2 features. That's tip bearing and side friction. And there are about 6 different formulation methods in the world today, of which we use 2 or 3 predominantly to establish the pile capacity. We combine the tip bearing and side friction together with geo to analyze our pile capacity. Typically, a timber pile with a big end top of 12, a small end 6 to 8, we consider driven 30 to 40 feet is good for 25 tons. Now, they can be good for 40, but typically I'll estimate the pile capacity is 25 tons. And for those out there that are thinking about using dynamic pile testing with timber, it's not really a very accurate way to test timber because of localized compression failure at the tops of these piles, which have been impacted by vertical drift bending and decay. So you can see here, if you take a pile and do an axial test on a piece of pile, its capacity will give you way more than 25 tons. It's not just the pile capacity, it's the soil capacity, it's the geo report that combines with the timber pile to give you the capacity. And when we don't figure pile capacity right, as you can see here, they turn mobile homes into covered bridges. They take the ends out of them and they use the bay window for a bottle shop, and this becomes their next new covered bridge. Why? Because someone went along the riverbank and did a bore sounding, drilling a hole in these piles and established the thickness of the annulus incorrectly, calculated the capacity of the piles, and voila, the first heavy load across the bridge didn't make it because the precast concrete super they installed tapped all the capacity out of the piles. And so understanding pile capacity, both from a geo and from an actual pile capacity itself, is pretty important. Now, lateral and longitudinal bracing are important aspects of piles. When you get tall, rangy ones, we like to have lateral stability in both directions. Well, as long as you get your tower girt up out of the flow so the debris fields don't catch it, this is a good game. Lots of times you just can't put them longitudinally because of the river flow. But you can see here, and people ask me all the time, what determines where that sash is going to go and how many X's we're going to have both longitudinally and laterally? And the answer to that story, of course, is about the effective length, the degree of incline and plumb pile. Each of these piles will calculate out the different capacities, and a handy guide, you see, people can get at me if you want, I'll give you a couple of handy guides, but ARIMA has in chapter 7 a really good pile load distribution chart for taking off the pile load distribution based on plumb all the way out to batter. In these pile bents, as you can see here, this is in Richmond, British Columbia, outside Vancouver. So, you know, just like an old fella like me, I'm getting old. As I walk a little more feebly all the time. And what happens when you get old? You walk with a cane. Well, what's a cane do? Changes the effective length. Well, what happens with a timber bridge? You know, the older it gets, a little more weak-kneed, what do? You put more bracing. So lots of times if I'm restoring old timber bridges, I'll put 3Xs. You can see in the background, there's 3Xs. This one in the foreground here needs another brace. But you can see the 3. Now, people ask me all the time, what about grids, Dan? What do you think about grids? Well, I don't mind grids that go between the brace and the pile. The bolt goes through the center of it, and the grid creates an anti-rotation. But I don't know that I'm really keen on them if that grid system is going to puncture the treatment. And secondly, it's always good to remember that in most cases, lateral braces only work in tension. Remember that, only work in tension. They don't really work in compression. They'll buckle. So it's about the tension side that gives you the rack resistance in a pile. What's rack resistant? It's the keeping within square to give you lateral stability for nosing loads. When you're going across the bridge, the truck driver's moving his steering wheel left and right. That's creating lateral loads through nosing loads. Trains, the train hunts back and forth between rail. That's a nosing load. So for example, in the rail, they just use a number. They assume 16th of the live is nosing, and each bend has to have a 25,000 pound load laterally applied to the bent cap top as a way of establishing capacity. And these things will drive your bracing design. Sometimes the bracing can be tall and rangy, and sometimes there's no longitudinal at all. You can see here differential settlement in a meandering oxbow river has led to a buildup of load here, a removal of load here. The bents are only supported at top by the girder. So what's it do? It rotates. There's only one solution, gentlemen, for this. You can't put longitudinals in here because the river flows. You've got to frame this bent. So you can see here more cross bracing going on, all over with tower girts and longitudinal braces as well. So back to the pumping piles. I said I'd return to it. As you can see here, they're measuring the pumping pile. You could put an accelerometer on here too if you wanted to measure what the pumpers were doing. But one of the things we should know as an engineer, never spec a shim for a pumping pile. The last thing you do to this is shim it. Engineers in the room, I'm going to say it again. Do not shim a pumper. What does a shim do? Well, it just drives it deeper. And this is shimming on steroids, none of it working. Look at this in BC in the Peace River area. You can see it here. Look at the circles. Shim them, they fall out, they get lost, they put new ones in, just drives it deeper. If you want to solve a pumper, cut it at the ground line, reuse it as a posting pile, and create bearing and increase capacity through bearing, frame the bent, sill the bent. There's a lot of different ways to fix it, but one of them isn't shimming because it doesn't work, as you can see here. Shimming just doesn't work. And ditch the meltoid. Don't use meltoid between wood layers, only use it between concrete and wood. It doesn't work here because this vertical drift pin lets the water flow down. It stays in the bright. This holds the water, doesn't let it evaporate, and away you go to decay. Let wood breathe. That's always the case. Let it breathe. You can see the effect of a pumper here with a shear failure. And you can see what went on here when they replaced it with a precast. We talked about it earlier. So timber girder design. Well, oftentimes with timber, we think of deflection as driving the equation. And on the highway side, we're governed by L400 on live. We camber out dead, typically 2 times dead load. We'll camber it out. We just handle live. As you can see here in this big long pair of beams that have gone in the Milkish Bridge to lift it up, we put FEMs and put 35-meter clear span beams in there, rolled them in on tracks, and then blocked them up. And we used vertical rods down through the deck and nuts, and we basically lifted this whole bridge with these 2 girders 35 meters long and lifted it up. Well, I had control of these beams, and I know that an unreinforced beam fails at L90 to L120. I know that a reinforced beam fails at about L20 to L30. And so I let them take almost 12 inches of camber out of these beams and go flat by pulling this bridge up to a camber of 87 millimeters on a string line. And this bridge was literally lifted in the air by these beams that were light enough to roll onto the bridge with its existing 5-ton capacity. That's the trick right there. You can see how flat they are. So deflection does govern. We watch for deflection in our beams, and next to it becomes the moment resistance. One, serviceability. That's the service of the beam. It's a rate of deflection for a given load. The other are the sort of the strength limits, the ultimate limits, where we have proper composite adjustment factors between ultimate and their design. Now, talking about these designs for girders, oftentimes we see notches. I hope that none of you folks do it after you see this presentation. But we see notches all the time with no slope of grain. And abrupt differential stiffness leads to tension forces in here, perp to grain, the weakest in wood we talked about earlier, and voila, we get this reentrant corner cracking. Look at it. Everywhere you see engineers doing it, don't do it. Let's see if we can make this one play here. I don't know if I can see. I want to tell you a story about this particular bridge. It has 13 stringers in it. There's a train going across it. I'm underneath it. I don't feel like I want to be underneath it. You can see all of these notches were in these because 11 of the 13 girders had been replaced in the last 3 years. Thus why people don't want to use wood. And they thought they could solve it by moving the notch further out to the center. And nary a time did anybody think about slope cutting. Here's another one here. You can tell this is a freight train on a slow order. Now, can you imagine if this was concrete and it had every girder 11 out of 13 broken? Would I be underneath that bridge if it was precast concrete that had these defects in it? No one would be underneath this bridge. No one. Yet we say timber doesn't work. Yet we say timber doesn't carry the load. And when they screw it over by not putting a proper slope cut on a notch and notching too heavily, I can still be underneath that bridge. Would concrete do that? No. So when we talk about concrete being so much better than wood, you need to know your facts. Look at this one. Look at the condition of those girders, all caused by man-made defects, had nothing to do with timber. Nothing to do with timber. It had to do with the people that were installing and cutting notches in the piece. And look how short some of those notches are and still have the problem. I pray that every one of you guys that have been online today will never allow another notch on a girder without some sort of reentrant corner. Look at this one here. I'm going to go to this one. This is a high-speed rail. This is passenger. Look at this. It's still carrying the load. So this is what happens. They go right to failure from a reentrant corner crack. Look at them. They go right to failure. Because of what? They didn't do this. And why did this matter? Because it made a gradual change in stiffness, reducing the tension perp, which is wood's weakest direction. Slope cut your notches and don't make heavy notches. On to timber decking design. You know, timber decks can come in many forms: plank, nail laminated, glue lam. You can see this red bridge in Kamloops, BC. Very, very long bridge, one of the biggest and longest in BC. Put together with what? Oh, very typical design. 2x stock, CCA treated so that it's wet and horizontally nailed the whole length of the bridge. And as it dries out, it shrinks away and the panel, these individual lambs roll. You can't keep asphalt on it for love nor money because it's constantly changing in the dry environment at Kamloops. And this design just had flaws. Here's one up close. Look at it. They're rolling. Why? Because they shrink. Why? Because they make them out of CCA treated wood. Why? I don't know. Don't do it. That's why wood gets a bad name. This is a plank deck here on a transverse series of sleepers. And this is a glue lam transverse deck, dry, treated, oil-based post. And you can see all these gauge beams have a slot for shrinkage and expansion, and they cover differential movement from the tire loads between deck panels. Leads to sometimes reflective cracking a little bit, but what bridge doesn't have joints in it, even if it's concrete? It's not a structural issue, as you can see here. Another bridge here, Alderley in Brisbane, Australia. Had to go in 48 hours. And you can see the deck here, heavy skew in this deck, dropped into place. I showed you this one earlier, longitudinal decks. This is a longitudinal plank on a transverse cross bearer on top of steel eyes. This little bridge here is one I like. It's built in Sun Peaks up in BC. It's an L100 bridge that was built in the shop beforehand. Everything pre-assembled, shear panels for increased shear capacity, built up ends for bearing, had a transverse deck with a secondary longitudinal deck on it, treated with penta, post all machining. When it went to site, not one bright hole was made. And in addition to that, we didn't need a dry piles. We didn't need a cast in place of concrete. We used bearing footings. We can use bearing footings on 50 kPa soil if we have to. Compact, drop these fellas in place, put them into place, backfill, and the first thing you know, you can have a bridge in place in a matter of days. The truck can run on right away. You're not waiting 28 days to see concrete cured. You're seeing wood go into place and be used immediately. You can see here the running deck on the thing, the longitudinal secondary deck for replacement under damage, easy replacement, so you have maintenance. Now, this is the end of today's seminar, but next week I want to encourage you to watch because I'm going to show you how paper beats rock and scissors. And this is the tree grown inside a boulder, and we're going to talk about that as we talk about how to maintain bridges and maintain them longer and at lower cost. For example, crossband, as you can see here, bending of pile tops that have been vertically spiked and screwed over and bending them, how it just doesn't work. It didn't work for Grampy, you can see at the bottom, and it didn't work for his son. And with that, I'll leave you with that little question in your mind about what I'm talking about. And I appreciate y'all being here and listening today and putting up with me for 11 minutes longer than you're supposed to. Thank you. Any questions?
Okay, great, Dan. Thanks. We do have a couple questions here. The first one is in relation to last week's lecture where FiRP can either be used as a flexural retrofit or strength enhancement. How much FiRP is too much reinforcement to cause shear failure? And how well do we know the origin of shear failure values in the CSA 086 and bridge code? The slides 104 and 106.
Yeah, good. That's perfect. Look, that's a multi-pronged question here. I'll take time to answer. I happen to be the subcommittee chair on Part 9 right now as we're revising the shear values in Part 9 to bring parity to 086. So hope is on the way. If you want to know what I use, even when I designed the Part 9, I use 086 as unit shear value, just for interest's sake. That's what I do because there's no reason that we've been able to find for its reduced value to 1.2 or 4. And so basically that's going to change in this next code cycle, just so you know. How much RP is too much to cause shear failure? Look, when I was testing some 3,000 reinforced glue lam beams for my initial code submittal back in the 90s, we would use 1.5% by cross-section RP. and bring about shear failure in every beam. That's how we realized that beam shear had very little to do with small block compression block shear, and that we needed an adjustment in our shear values. And I was the first one to get 290 or 2 MPa in horizontal shear for glulam beams in America, and the rest of the industry soon followed. And it came out of empirical test data. In the second code approval, 6046, we were allowed to go down to about 0.2% by cross-section, as long as there was RP, basically, that would shut down localized defect failure in the bottom tension face. Then we would usually see some sort of shear failure. Of course, it depends on the beam size and the span, of course, and so on. If you have a long beam span, long before shear failure becomes a problem, you run up against your live load deflection limit, because obviously Woods E at 12,000 MPa or 2 million PSI, for example, is lower, and stiffness is a factor. Another thing we're working on in Part 9 right now is load distribution factors, which, as you know, in Part 9, or some of you may know, is not really easy to interpret. It really doesn't have a place to use transverse glulam panels. And we're in the process in this code cycle of developing these load distribution factors. And we do this ourselves because we test using string pots the different deflections by placing loads at certain points over glulams. And we'll actually test what the load distribution is through measuring deflections in girders for different placement of point loads. And there's another little interesting feature that goes on, and that is that properly S-clipped, a glulam transverse panel deck can increase the global stiffness of a system by upwards of 30 to 35%, depending on your connector strategy and so on. So that's a little bounce that you'll get for your beams. So I hope that answers your question. You can have too much reinforcement because it'll cost too much money in your client or failure. Any other questions?
Yeah, just one other one so far. What's the optimal angle for a slope cut?
I understand you. Typically, the slope cut, we measure slope in 6 to 1 is my preferred. 12 to 1 is the point at which you see no loss due to tension perp effects. 6 to 1, you'll see about 92 to 94% capture, or prevention of tension perp effects. So I generally speak to 6 to 1 because they're easier to make and so on. But I'll tell you this, if you're out in the field, and I've got guys that don't know how to run a chainsaw or can't or don't understand or whatever, I'll even take 3 to 1, because I'll tell you what, 90 degree on a notch in most girders is going to lead to reentrant corner cracking before you're into the system 2 years if you get any amount of heavies. It's just the way it's going to be. And it'll be the end of them, because it depends on whether you get the butt end of the tree if it's solids on, or the tip end, as to whether that horizontal reentrant corner crack precipitates up into the girder or away from the girder. And typically they go right up into the girder and kills it. Other questions?
That looks to be the end of the questions. So I think we'll just wrap it up there, Dan.
Yeah, good.
Oh yeah, if you haven't already, sign up for register for the next webinar, which will be next Tuesday at 2 p.m. on maintenance of timber bridges.
Yeah, it'll be interesting. We'll talk about, as I said, how paper beats rock and scissors. And so that's a kind of an intriguing point. We'll have a chance to think about all the things that drive maintenance in our timber bridges. And what's going on right now is asset managers are tired of timber bridges. Why? Because they send maintenance workers out to fix timber bridges as if they were steel or concrete, and they're not. And when they go out and fix timber bridges with the wrong MO and the wrong methods, what happens? Within 2 or 3 years, it's broken again. And asset managers are sick of it, and they live for the day they can get rid of the last timber bridge. And because of this, because of these strategies, for example, like New Brunswick, the difference between New Brunswick and Nova Scotia right now, the senior engineers at DTI New Brunswick don't believe timber bridges, new timber bridges, greenfield timber bridges, are the right way forward. In Nova Scotia, they've passed that. They've gotten on with it, and they believe they are. And they're speccing timber bridges in their tenders all the time. And in BC, they are. And in Saskatchewan, they are. And in Ontario, they are. And in New Brunswick, we just have to get there. And what's causing this? A lot of it has to do with misconceptions that timber bridges don't last, which is wrong. That snow plows tear up the curbs and beat the bridges where they wouldn't a steel and concrete one. If you got a girder under bridge, I don't know how the snow plow gets at the girders. You know, there's a lot of misnomers, and it's really just unbelief that timber bridges can do the job. And my whole mandate today at this point in my life is to change that unbelief and help people to see that fact is stranger than fiction. Thanks, guys.
Excellent. All right. See everyone next week.
See ya.